Oh, what a day! What a lovely day!
Welcome to Flat Earth QED. I'm your host, Nathan Oakley, and if you're new to this channel or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. If you would like to support this channel, there is a super chat that runs alongside each of these live shows, and there's also a PayPal link in the info box below this video. Joining me this evening is YouTuber Good Times for All, which is GUDTIMS, number 4. All. How you doing, Zach? It's very good to have you here. Zachary Sabala to some.
Well, thanks, Nathan. It's very good to be here. Having a wonderful day so far.
Excellent stuff. So, I don't know, it's probably a good idea to have a little chit-chat before we launch straight into the heavy-duty perspective stuff that we're going to be discussing tonight. So, I know you've just literally been telling me about some quite exciting things that are going on in your life at the moment. I don't know which bits you want to divulge to the public, but maybe we can start with a bit of you. What's your bag in Flat Earth, and what are you doing currently?
Well, I started all this because I had been looking into the flat Earth, and I came to the conclusion that I could not find a curve or any movement. And I knew we've been lied to, for so long about so many things, but they've been able to hide it from us and sweep all these things that they're lying to us about under the rug. And when this came out, it hit me that they can't hide this from us. This is right under our noses. They can't sweep it anywhere. And that's what made me start this YouTube channel. I just wanted to show people, not so much that the Earth isn't a spinning ball, but just that we are being lied to. That's my main thing, is that we're being lied to. I mean, the fact that it is not a spinning ball, it helps greatly to prove this point, but the whole thing for me was to get the fact out that there are a group of people. It's a conspiracy. The word conspiracy means two or more people lying to you. And that's all a conspiracy is. And here in the United States, the CIA has termed the coin conspiracy theorist as some kind of nut job, when in reality, it's just a person that can see what's going on. But yeah, most people don't even like the word conspiracy because they consider it to be, taboo. Just like the word anarchy and other words, that they've switched around. But that's pretty much the reason why I started all this, because I know we're being lied to, and this is something that I can show people, and they can't hide from us.
Fair enough.
They can't say, "Oh, well, yeah, that's how I got started and why I got started."
Can you tell us about there's a video that we covered on the debate fairly extensively, fairly recently, which was in a warehouse with some paint can lids. Can you tell us about that? Because that's a good lead into the subject we're about to cover.
Yeah, I actually, I was wrapping my head for over a year. I would gone out to Chicago or Michigan City and seen the Chicago skyline multiple times. And on multiple different occasions, I could see different amounts of it. And I knew it wasn't curved, but I wanted to know why this was happening. I was really trying to figure out why the bottoms of things get cut off when the atmosphere is somewhat not to blame. I was trying to figure out what part of the atmosphere was causing it. So I thought it was humidity and we were looking at refraction. That's what I believed it to be. And then as I started experimenting in the warehouse, I figured out that even with a lot of humidity, one sec, down to just a little bit of humidity, I was still missing parts of the bottom, and it appeared to be just about the same. Even with the humidity and temperature changing drastically, the bottom part was being cut off almost about the same until the weather had changed drastically. And I had done multiple tests before I'd put out that paint can lids. And I had realized that it had to have something to do with the limitation of the lens. And I started looking into different things besides refraction. And I had come across diffraction. And once I figured out that it was this certain, because there's 6 types of diffraction. And once I figured out that there's one that affects things right along your eye line, things started falling into place and clicking. And I started, I mean, it was about 6 months of research, before I actually put out my first video saying, hey, this takes place everywhere, and there there is no lens that doesn't have this, as long as it has a circular aperture. Um, and I figured out that no Earth curve calculator uses this, that this should be added to every Earth curve calculator. There was just so many things that started adding up, and it kind of died off there for a while. I remember you made a big deal about it. That was the first live show I ever did. It was right after the paint can lid. You had me on Flat Earth United, and I
Yeah,
came and
I
we
mean,
talked about that and a couple other experiments.
it was seriously important that people started to get a grasp of this, because essentially it explains why things disappear from the bottom up.
Yeah, and I still didn't quite understand it. I still wasn't. This has been a very long journey for me, actually, the whole diffraction thing, and not until I started talking with Chris Van Matre and Gav, or Vortex Puppy, and then a gentleman from Australia named Glenn, Orbic Fudpucker, as he goes by here on YouTube. They started sharing with me some different ideas of looking at perspective, about keeping the plane flat instead of having the ground come up to your eye level and the sky come down to your eye level. They kept those things flat and they arced the eye. And that just blew my mind and started making so much more sense. And then it made the diffraction even, I understood how it happened. Because before it was like, yeah, it gets so far away and the angles get so small. But this, you can look at it and you can see mathematically and calculate it mathematically how much of the bottom is going to disappear and how much sooner it's going to disappear than the top. And yeah, it's coming full circle. It really is. There is no, now I'm not saying that there isn't any curve at all. I've never said that. I'm under the impression that water lays parallel to 90 degrees from whichever way the electric field is flowing. And I mean, you've seen a lot of my videos, Nathan. I'm still not even sure if the sun is moving. There's a lot of stuff up there that we don't know. But now there's a test I'd like to just talk about for 1 second. This one that Jaren's planning on doing with this fishing line type stuff.
Force
I
the
think
twine.
this is the
A
greatest
troll
test.
came up with that. Force the twine. Do you like that?
Yeah. Oh, I love it. Yeah, that's a great catchphrase there. But I think this should be done up and down every coast of every continent, east and west and north and south, and we could actually start finding out if there is any curve to our electric field. Because I don't think we would even notice if there was like a bell shape in the middle, like when I bent that water. If it actually looks like that, I don't think we could notice. It could be 1 inch per every 10 miles that it bends. We definitely know it's not what they say it is. But to say that it's perfectly flat, I can't do that yet. Because I have done experiments where electricity bends water, and we know that there's electricity above us and below us, a positive above and a negative below. And yeah, there's still a lot of experimenting to do and a lot more thinking and more ideas to be sharing with people. But it's coming along. It is. I'm so glad that diffraction is getting out there. I've heard it, multiple people say it. And I love that. It's been a long year, I'll say. But yeah, I mean, these things take time. You can't figure something out and expect everybody else to just take your word for it and run with it right away. I know that's how we all want it to happen, but it's not that. Things happen organically, I've come to find, especially with flat Earth. It's so good that these things are happening slowly and taking their time, in my opinion. I think if too many people were to wake up all at once, it would probably be a bad thing.
Possibly.
Yeah, I think anger is one of the feelings that people get when realizing all this stuff. They find out that they've been lied to, and I don't think 100 million people all mad at NASA would be a good thing all at once. We don't need people storming, down to Houston and burning down the buildings and stuff. We don't need any of that. That would push us backwards.
I agree. It looks like we've been joined by
But
Sleeping Warrior just at the right moment, because I've just popped your we've got resolution and the Rayleigh criterion on screen, so that's like the first slide. I don't know if you want to start. I'll just say a quick hello to Anthony. How you doing, Anthony?
Well, I wasn't here before, but I kicked myself.
Excellent. So let me know when you're ready, Zach. I've got the first slide on. I'm not sure if this is actually the one you want to start on.
yeah, we could start on, this will work.
Okay. Just let me know when you want to spin on, and other than that, I'll keep my mouth shut.
Okay, I put this slide in just to give the definition of resolution and the Rayleigh criterion and it's very important that third word in there, circular, for a circular aperture. Now it changes a little bit when you get into other types of apertures. They have square ones, rectangle ones, but most cameras, your eyeball, and almost every telescope has a circular aperture. And this is what the Rayleigh's criterion is, an Airy's diffraction is pointed towards, a circular aperture. So when you have a circular aperture of a diameter of any size, the minimum angle of resolution is that little radian sign there, can be figured out by the Rayleigh's criterion. And that's the little, there at the bottom in the green, the little circle with the line through it stands for radians, equals 1.22 over lambda, which is the wavelength of light, over the diameter of your aperture. Now the 1.22, I was actually trying to look up to get a slide to show what that stood for, and I got all kinds of people saying that Rayleigh just threw that in there and it doesn't really stand for anything, when I know for a fact that a year ago when I was doing all this, I might have to check my old videos. I know I had one that said 0 is a zero vacuum, 1.22 is pure nitrogen oxygen based atmosphere, and then 1.33 is water. Now they did this because atmosphere plays such an effect that they can only make the limit. So they have a perfect nitrogen based atmosphere, and any more moisture, dust, humidity, wind blowing, there's all kinds of things that can mess with it. The angle will only get bigger after that. So that's why they call it the angular resolution limit. Next, please. And here is just to show that you can go to any university pretty much in the world, I bet, and they have papers on Rayleigh's criterion. Here's one from Harvard. It even shows you how to set up an experiment to do this. The important part is right down here. It just shows in the comments, Rayleigh's criterion is usually applied to circular apertures, where the common resolution is when the center of one Airy's disk pattern falls into the first minimum of the Airy's disk pattern of the second source. And then it shows, I just wanted to show that the equation always stays the same. Radians equals 1.22 times lambda, or wavelength of light, over the diameter. And like I said, again, you can go to any university and they will have papers on this. It is a very well-known, it's taught in beginner's physics. Okay, next. And here we get into how light is perceived by an optical sensor with a lens with a circular aperture. It creates right there, which was figured out by George Airy's, actually the astronomer royal, and a single pinprick of light will create what we have there, which is called an Airy's disk. That red, it almost looks like a set of bullseyes up there. Now, we've all seen this. If you look at car lights really far off in the distance, it creates a big circle. And then as it gets closer, you see that the circle actually gets smaller and smaller and smaller until you can actually make out that light. On the right, you see what it would look like in a 3D or from a side view. Now, as you see above the 3D point where it goes to the 2D, the X and Y, on that X-axis there, any of those lines dipping below that X line will not be seen. And that's why you get the bullseye effect there. So that's just one pinprick, one point source of light, and how we would perceive it with any optical system with a circular aperture. Okay, next please. And here it's more of like a 3D. You look up at the top right. That's how it looks, a real source of light. You have there at A. And as you look at B over here, there's the one source of light there coming up. And then they add another source down here at C. And they are completely resolvable. And then you look at D. Now that right there is the angular resolution limit. That is the limit of where both of those little nubs can be resolved. And then as you see to the right, they kind of merge together, and that arc in the middle, that little bend that drops down, disappears. So these two light sources now appear as one light source. Next, please. In this slide, it's going to show us the same thing, but it actually gives us a visual representation of what the light sources actually look like when this is happening. You have your one on the left there. You can see at the bottom how it is fully resolved. And then as it gets to the second one, the light sources start bunching together as they're almost melding together. They're not two perfect circles anymore. It's like a circle and a circle with a line in the middle, and they're kind of scrunched in. And then as you go over to the right, you can see how they become fully blended together and will make just one light source there at the top. Next. Okay, now this is how an object, see the apple when it's real close to your eye, it takes up 20 degrees of space in your eye. And as you move the apple away from you, you can see the lines that it takes to connect from the top and the bottom get much closer together. And that's perspective right there. Things getting farther away take up less space on our retina. And they appear to be smaller. Even though they're not, it's still the same size apple. As we move it away, it appears to be smaller. I just wanted to show the angles there and how that works with the eye. Okay, next. Oh, we can skip over this one again. Okay, now here's where it gets into the weather and how the weather is going to affect how far you can see. People will say, oh, well, that doesn't work because you can't even see the buildings over there at all. You can't see across Europe or to Europe from the United States and this and that. Well, they have a thing called the meteorological optical range. You find them at every airport runway and every harbor where there's, ships coming in and out. It lets you know how far you can see due to the weather. And it starts off, of course, at 0, dense fog, less than 50 yards. And as it works its way up to exceptionally clear, which is 27 miles plus. Now you got to think 27 miles plus, that is well over the curve there. But here it says you can see exceptionally and now those are very, very rare days. The 9s, the 8, I believe it was an 8 when I was getting those pictures of Chicago that one day when I could see all the buildings along the thing. That wasn't even a 9, not even an exceptionally clear day. So your vision is going to be cut off by atmosphere eventually. It doesn't matter if you have the biggest lens in the world, enough atmosphere is going to block it out. And the more atmosphere you're going through, the bigger your angular resolution limit is going to be. So if you're at 35,000 feet in a plane and you're supposed to be able to see, 270 miles, but you can only see 200 of them for some reason, it's probably because there's so much atmosphere in there that your angular resolution limit has gotten so big, and it might even look like the horizon dropped, the apparent horizon. but it all has to do with how much of the view on your horizon is going to be distorted from the atmosphere. So this plays into part in so many different ways. Next. And this is just a source anybody can go to. Every observatory, at least in the United States, I know, probably in every first world country, every observatory will have one of these. This is called a astronomical seeing chart. Now, a seeing chart will give you every direction of the night sky, the cloud cover. There's 4 that you do in the sky and 3 that you do on the ground that can affect how well you can see. Now, if you go into an astronomical seeing chart, there's a lot of things they tell you about it, about what you're reading and how to read the chart. And it'll tell you anything below, I believe it's, oh, I don't want to be quoted, so I'll just say 25 to 35 degrees. Somewhere within there, no astronomer takes any or collects any data below that, because the atmosphere starts getting denser and thicker and starts affecting what you're seeing that much more. And you can't use it as scientific data or well, I don't even want to say scientific data. You can't use it as any type of data because it's not trustworthy. The atmosphere is going to be bending it and moving it in so many ways that they just don't use it for observational data. Now, if you look, of course, cloud cover will affect what you see in the sky. Transparency, kind of the same thing. Now, seeing is a little bit different, and it's not just wind, but the air is a fluid. Just like our water is a fluid, the air is also a fluid. And if it's flowing nice and slow, just like a nice brook or a creek going by, if it's flowing nice and slow and it's only a foot deep, you can see the bottom no problem. It may be off a little bit from refraction, things like that, but you can see all the way down to the bottom and you can count the fish and the rocks. Now, if the water is rushing a little bit faster, it might be a little bit harder to see. You'll see waves in it, you'll see ripples. And when it's white water and running real fast, you don't see the bottom at all. That's what seeing is. And then, of course, there's darkness, which is light pollution. And then, of course, along the ground, they have wind, humidity, and temperature, which can also affect it. But the main thing is they'll tell you the closer you get to 0 degrees of the horizon, the more and more the atmosphere is going to make your angular resolution limit larger. Now, when they do this, they don't mess with the 1.22. They actually will alter the size of their diameter, and they will make that smaller. It tells you how to do it in there. I never really got into it because they didn't really get into it too much along the horizon. The way they were doing was up to a certain point, and I don't know. After it got into atmosphere and how the atmosphere affects it, it's so hard to tell what the atmosphere is going to do that I kind of just dropped off right there, and I'm stuck on the limit, what the limit will be. Okay, next. And this one here, this just shows how the bottoms of things cut off when the top of an object is further away from the eye than the bottom of the object. Now, if you flipped it over, it would happen the other way. The top of the object, if you were really high up and your head was, say, along the ceiling, and you put something on the bottom of the floor and something on the top of the ceiling, you would see the one on the bottom of the floor much longer than you would see the one at the top of the ceiling. So this doesn't mean it just works this way, the bottom up. Now, the little yellow line, that little arrow or triangle in there, we're going to call that our angular resolution limit. So anything above the black line in yellow and below the black line in yellow will be equally cut off. Now, as you see, these are all separated equally, these red lines. And as you see the angles that are coming to the eye, as they cross that first red line there, you can see the angles at the top are much further away from the yellow part there, the yellow triangle, than the bottom ones are. Now, if I kept on making these lines go out indefinitely, eventually the lines would converge on the yellow triangle. They would become equal with it, and then inside of it, once they get to that yellow triangle, everything within that will be cut off. But as you can see, the ones at the bottom will reach that angular resolution limit much quicker than the ones at the top, allowing the ones at the top to still be seen because of the angle of attack. So not until they reach a certain angle, and it depends on the size of the lens, the size of the aperture, and what light source you're looking at. But like a human eye, inside somewhere, regular lighting will be about a 0.02. And then if you're squinting at the beach pretty far away, it'll turn into maybe a 0.038. Now, a 0.038 at just 3 miles away would cut off 4.5 feet above and below your horizon line. So if you were standing, and that's with a perfect atmosphere. So if you were standing 3 miles away looking at an object, you wouldn't be able to tell anything below 9 feet. Or, yeah, 4.5 feet below your eye and 4.5 feet above your eye minimum. So for that 9 feet there, that's why you see the top of the sailboat and you don't see the bottom. It's because of this right here. It's how it all works, and it can be proven mathematically. Yeah, this isn't the only reason, of course. I mean, this is the main reason, but then there is also looming and different things refraction can do, and this is the one that is definite. This is a fundamental limitation of every lens with a circular aperture. We can figure this out. As far as calculating in the atmosphere, I've looked into some of the meteorological optical range charts, and the mathematical equations use just about every letter in the alphabet, and it's just way too far beyond me. I'm not even going to attempt any of that stuff. But yeah, this can all be proven. It can all be scientifically calculated, and there is no way around it. And even if it was curved, you would have to add this to what you're looking at. And not one flat Earth curvature calculator adds this in.
Well, can I first say, excellent presentation. Really, really good.
Thank you.
There's a couple of things that I raised when I first saw this on IRM, and you agreed with me then, so hopefully you'll do the same now, which is to just basically summarise, in essence, but with some examples of things we've seen prior to now. So hopefully I can get my mouse so that you can see it as well. Can you see that mouse?
Let me see. Yeah.
Brilliant. So if we pretend for a moment that, as you said, these lines are getting narrower and narrower and narrower, obviously when you get out to significant distances, say between 15 and 25 miles, the angle to the bottom of, say, a turbine will definitely sit in this band, because it has reached the limits of the angle that you can see of the bottom of the turbine. Now, because the turbine is obviously not the only thing, the bottom of the turbine is not the only thing you can see the top of it as well. You would see the top of the turbine with the bottom section cut off. Is that correct?
Absolutely.
Right. I knew that would be the answer, but yeah, great. So the next thing is waves. So you've got, again, the same principle. If you have a wave in this vicinity and pretend this is a 5-foot eyeball, well, not a 5-foot eyeball, an eyeball that's 5 foot off the ground, not a 5-foot eyeball. Obviously, any, let's call them 3-foot waves, are going to be not intersecting the midpoint. And obviously, as they go further and further out, they are going to be, by forced perspective, brought closer and closer and closer to the midpoint, till eventually, by, again, the fact that you have a narrower viewing angle to something that is essentially on the same plane, this line on the bottom, it will eventually reach the point, by virtue of perspective, where a 3-foot wave that was well below your eye line at this angle will be above the midpoint, because of perspective, in the far distance. Is that also correct?
Absolutely. That is absolutely correct. Yeah. It all has to do with the angles, and it can't be avoided. Yeah, thank you for asking those questions, because they are important. And a lot of people, I forgot about the wave one. I remembered the first one, but I've forgotten about that wave one. Yes, that's a great example.
So in
and why we
essence,
see it looks like a curve and it looks like just waves there, but yeah, it's just
and
being
by no
cut off by the
coincidence,
angular.
this directly translates this calculation to the refracted hidden value contained within the perspective denying proof of nothing curvature calculations that they present based on the standard model using R.
Mm-hmm. I'll give you an example. At 10 miles from 5 feet off the water, on the curve, right, there should be 35 feet hidden from the curve. And then you bring in your 7.6R refractive nonsense, and it probably gets somewhere about 25 feet, maybe 27 feet, somewhere around there, maybe. I'm just taking a stab at it. Well, at 10 miles at a 0.038, you get 34.5 feet cut off. And then if you're 5 feet off the water, you would have to only use 17 feet of that plus the 5 feet. So it would bring it right to about 22, 25 in there somewhere. And you got to add a little bit for the atmosphere. So yeah, all they did was reverse engineer this and say that's how big the Earth is.
Would you also agree that this is thoroughly debunking geodesy?
Oh, absolutely. Yeah, there's multiple things that debunk geodesy, but the fact that they use a theodolite and they're trying to measure things with that little tiny lens and aperture at that distance, that's nonsense. Of course, there's going to be a whole bunch blocked off by the angular resolution limit. And when I looked into the equations, I did not see anything that had to do with calculations for this. I mean, they use calculations of the stars in their measurements, which is just nonsense when you're measuring the ground. But they don't use anything for the optics of that they're using to make these measurements. No, I believe geodesy is a joke. The whole thing is constructed. It's mathematics. That's all it is. And I mean, surveying is amazing. The things that surveyors do, but then the geodesists take what they do. Like a surveyor will take what he measures and he actually has to shorten it. He takes his measurements and on a scale of 1, he makes them a 0.099913 something or something like that. And then when a geodesist gets it, they go up to and scale it up to a 1.111654 or something like that. And they actually make the arc right there, mathematically. There never is a measured arc from a surveyor. They don't measure them. And yeah, Chris Van Matre was showing me this. He figured all this out not that long ago. But yeah, they'll be doing a video on it here pretty shortly, I think. But yeah, geodetic surveying, imagine that. It was founded right around the time that Cook got back from his expeditions, showing that going around Antarctica took him 3 years. And then all of a sudden in the 1700s, they started doing the Institute for Geodetic Surveyors. So yeah, I see it as being a major part of the deception.
And they're in essence taking points, and then that just is their starting point. That this is the real surveyors, the people actually building things. You know, they do cross-reference these points that are laid down by geodetic surveyors, but ultimately that's just a starting point. From there on in, they're basically surveying and building on a flat plane.
Yeah, absolutely. They never take into account for the curve.
No, because there isn't one, as far as I'm concerned.
Yeah.
I know you feel differently. There
Well,
may be
if
one.
there is one, it would be. It's not what they say it is.
Sure.
I would love. I want to know. I really do. You know me. I'm big into electricity and stuff like that, and I think electricity controls everything, and that would be the best. I think this experiment that Jaren's getting ready to do, I hope it shows a little bit of curve. I'm hoping it does, either one way or the other, either concave or convex. I think it will force us to get out there and actually start taking these measurements. And I think this is probably the best one I've seen so far. Force to twine. I love that.
And you've got to do exactly what you've said. You've got to kind of put your money where your mouth is when it comes to that sort of test. Obviously, it would have to go perfectly, but ultimately, it would show either way what it was. There's no ambiguity. If it's done correctly and it dips into the water, then it's curved. If it's above the water and dangling out and dipping in at the edges, which seems unlikely, but then again, you just don't know. It might be concave. You just don't know. And this would show it either way. But I noticed when it was first sort of talked about, at least on my show when Jeremy was there, a lot of the ballers in the comments were like, I'm not interested. This isn't a good test. And you think, questioning your faith maybe? Because I would be happy to stick my money on the line, or, and say, if this showed curvature, I would absolutely reassess my position in a major way.
Oh, yeah. We're going to all have to if it does. And of course, I'd like it to be done multiple times in every place it's done. I like to experiment a few different times before I call something a fact. But yeah, I think this is going to be a really good one, a telling one. And once it gets started, I think we need to, if it shows anything, even if it does show flat, I think it should at least be taken to a couple other places on the plane and attempted as well.
Sure. Are you there, Anthony? Did you have any comments?
Yeah. What I want to know is, when it comes to the day-to-day battles with the ballers, they always use the curve calculator. And mathematically speaking, as you said, they don't take into account Airy's diffraction. And we know that they don't take into account perspective. They've essentially hijacked perspective. From a mathematical point of view, what is the correction that would be needed on the curve calculator to take this into effect, to take this into consideration? Because they always, well, did you take into account refraction? So it makes sense to me that we should counter-ask them, well, have you taken into account the Airy's diffraction? And the answer, of course, will always be no, because they don't even take into account perspective. So my question essentially is, what's the effect on the curve calculator, and what should we do about it in terms of telling them that the curve calculator is not addressing this?
Now, the way they always have us looking at the sphere is standing on it and looking down to the edge of the ball. You know how they have that slant? It's never straight off. We're never looking straight off into space. We're always looking down towards the edge of the curve as far as we can see it. Well, if that's our horizon line right there, then we would take that distance, the distance from the object, and then just measure the top of the angular resolution limit. You could probably cut off the bottom half and say that's cut off by their Earth curve. But anything above that, you would pretty much slice the angular resolution limit in half at that distance and add that on to their Earth curve calculator.
What would the effect be?
Let's see,
Go on, sorry.
At 10 miles, it would be 17 feet you would have to add to it. So it would definitely negate their 7.6R.
Yeah, specifically,
nonsense.
it's a reflection of the refracted hidden value.
It's a reflection of? You mean the opposite of?
Yeah. So what they have co-opted in this respect is the value that you lose at the point of convergence. Therefore, what they are calling the horizon. So where you get the figure for what is being hidden is from that horizon. How much is the obscurity caused by what we call the hard horizon? What is that value? Well, in the calculator, it's the refracted hidden value.
Yeah, so we would just add to that.
So basically what we can do is they always immediately go to the refracted hidden value. But what we should do is say, actually, the refracted hidden value is Airy's diffraction. We need to take that off, not add it. Is that right?
Yeah, I would say that's a fairly accurate
yeah.
way of describing it.
Okay. And the best way to take your pictures, don't zoom in all the way. Have your aperture as big as you can get it while still being able to kind of see the object, and you will see more of it. I learned that watching Ranty, how he would aim up the buildings a little bit, and it would show him more of the bottom because he's changing the angle of attack. It's no longer directly in front of him.
That was my suggestion. So I said to him after he came back from looking at I've forgotten it, Barrow and Finesse. And I said, exactly that. I think it was after watching one of your videos, actually, Zach. So it's, you know, it's I won't take full credit, but ultimately I said to him exactly that. If you can angle your camera up, you'll force the midpoint up the frame, because currently, if you're 90 degrees or close to 90 degrees and you're a foot off the ground, half of the camera frame, it represents a foot of elevation, and you've got, what is it, 18 miles of distance and a foot of elevation. So you've got a tiny angle in half the frame. It's like, but if you angle your camera right up, suddenly you've got all of the frame with a wider angle of view from the bottom to, from the mid of the frame, or the mid of the lens to the bottom. That will increase your angle, and it worked. So he seemed to catch more from like an inch by angling his camera up.
Yeah, I think we should all start doing that. When I was out there at Chicago that first time, when I got those great pictures, and I got the lights along Lakeshore Drive, I was doing that. I noticed that because it's not right along the horizon. There isn't a bunch of water or anything beneath it, because there was a big concrete block there in front of me, and I wanted to get the concrete block out of the way. I didn't do it on purpose. I wasn't planning on doing this. I just aimed up to get as much of the city in and as much of the sky as I could. And I saw the actual 38 miles away. I saw lights that were no more than 100 feet off the ground.
Cool.
And that should be impossible.
A lot of credit must go to Ranty, because it's all well and good me saying, oh, I suggested him doing that. It's the boots on the ground actually doing it that achieves the shot, not me suggesting it. So, 1% me, 99% Ranty.
Yeah, he definitely puts in the time. That's what kind of people we need. We need people that are going to go out there and make the observations and share them, and not settle with something. I'm sure he's probably going to be out there again here this week. Even though he knows what's going on and this and that, there's always more to learn about this stuff. We were just stumbling onto this stuff, and I know there's a bunch of stuff I probably overlooked. But we're going to learn. There's a lot of research. I'm going to be doing a lot of research here soon. I'm going to have some time on my hands. I'm going to do some camping here. Me and my dog are going to go camping for a while, and yeah, I'm going to get back into research mode.
Zach,
yeah,
have you heard the recent conversation about water and whether I know it's off topic slightly, but I'm going to ask it anyway.
Yeah, absolutely. I actually got a nice tutorial on it last night by Mr. Adam Meakin, the Adam Meakin.
If I said to you that water was an element in its own right, would you agree with me? As opposed to a compound made of hydrogen and oxygen.
Yeah, I don't know. I mean, we know water will turn into a gas, and we know it will turn into a solid and a liquid, all within the shortest temperature range of any other substance, any other liquid, any other substance. Water is the only one we find in solid, ice, and gas in the temperature ranges here on this plane. So it's special in its own right. Now, to pick it apart, I've never done any experimentation with it. So I'd be going on what I've read, and that's just what I've read. So
yeah.
So commenting, it's not my place, but Adam, the way he explained it to me last night, I could see where some people were making misconceptions about how it all works.
Well, I'm not even sure I even get his point, but his point appears to be that he says that water is an element in its own right, and you cannot get hydrogen or oxygen from it. You need to do more stuff to it, which is true. You do need to add an electrolyte, but he thinks it's an element in its own right. It should have its own place on the periodic table. And
to separate hydrogen and oxygen, you need something for the oxygen atom to combine with, because an oxygen atom itself is very unstable. Even O2, two oxygen atoms, is unstable. Not until they find that one hydrogen. That's why oxygen will connect to anything as quickly as it can. And now separating it is difficult. That's a difficult part, because it wants to be connected. It's attracted to becoming, because it has, they say, the two electrons I'm not certain about all the electron, atom, nucleus. I don't prescribe to that because I've never seen any of that. But I understand the charges, how electric charges work. And if you just want to say it's an element with a certain charge, that makes sense to me.
Good stuff. As this was mainly about diffraction, though, is it possible,
Yeah,
before
sorry
we
about
round
that.
out the show, for you to give a quick summary of what you've just told us? I'm not going to put any pictures up, but if you can verbally do it, that'd be marvelous.
Yeah, along the horizon line, no matter where you're looking, even if you're looking up into the sky, remember this was all first done with astronomy, where they were looking up. Um, every lens with a circular aperture, no matter how big it is, has a limit to where it can resolve one light source from another. So that means when you have two lights, the further away you get from them, the closer together they will get until they merge. And eventually, they will get out of your view completely. This happens on a flat surface. This happens looking up in the sky. This happens everywhere. This is a fundamental limitation of a lens. You cannot see forever. No lens can. So when you see a curve in anything you're looking through, if you think the bottom's being cut off by a curve, you need to get out a calculator and stuff like that and punch this in first and try to, the best way to do it too would be over short distances, because the more atmosphere you have, the harder it's going to be to calculate all this. I mean, we should be able to see a curve within 3 miles with the cameras we have. So
Totally
I'd start
agree.
off there,
I totally
and you
agree.
won't have as much distortion. But yeah, this is every lens with a circular aperture. This is a fundamental limitation of them, and it cannot be avoided.
I don't know if you saw it,
And yeah,
but Block for Block did an example in his modelling program where he showed the effects of the horizon versus someone's eye level, i.e. the person walking away from you's eye level as they got towards the horizon. And the effect was profound when he showed it. And I was like, wow, yeah, you really would see the ball quickly if we were actually on a ball. Same applies for going up in elevation. It would become immediately apparent, as soon as you started
yeah,
to raise. But conceptually, people struggle with that, and it gets met with "don't be so ridiculous," or normally an ad hominem attack on whoever's saying it. But ultimately speaking, I think the best easy depiction of this is probably by Rory Cooper, My Perspective, who showed it years ago, literally years ago, with the comparison side by side as what you would see rising up on a flat plane versus rising up on a ball, and the angles that would be generated as a consequence of that raising in altitude. And that's in essence what we're talking about here. They're telling us with the calculations that we have a curvature, and in reality what we have is obstruction due to the effect of angular size reduction at distance. And the effects are to say that you would lose things from the bottom up on account of the fact that at the bottom they are at the most reduced viewing angle possible at a given distance, obviously taking into account that you would also have atmosphere, so the quality of the day does come into it to a massive extent. So all these things combined would give you how much you would or wouldn't see at the bottom of something, depending on the clarity of the day and the angle of attack to that bottom section of whatever it is you're looking at. And the bottom will disappear first. Simple as that. Nothing to do with curvature. And to compound this problem for the people who have a ball belief, this is absolutely and completely omitted from the begging the question proof of nothing perspective omitting curve calculator. I think that's redundant. I think I said that twice. But either way, the R-based model that people think they live on excludes these details completely.
absolutely. Well said, Nate. I couldn't have said it better myself.
Cool. Anything you want to add on that subject, Anthony? If not, we'll round out.
No, to be honest with you, they're never ever going to accept it if you take away their refraction, their standard refraction, and there's not a lot we can do about it in terms of other than just telling them that we can take that back by virtue of this Aries diffraction, the limitation of the circular aperture. But they're never going to allow us to have it anyway. So I don't know how we'll ever get past that other than just demand it, and they're never going to give it to us. But it's like the perspective; they're never going to give us that either. So it's like the whole calculator is just full of nonsense. I don't even know how anybody can really cite it with any credibility. It's ridiculous, but it feels like we're banging our heads against a wall in some respects.
I don't think so. I think at the moment there's nobody coming in to present that calculation. They're all far too scared to, because they know that within seconds it'll get ripped apart on the basis that there's no scientific evidence for the R value that's used throughout the calculation. But further to that, it's nice to be able to show people who do understand that and do accept that it doesn't prove anything, how the magic trick actually works. Why are so many people convinced by this curve calculation? Well, if you can show them that it omits perspective, then that's in and of itself something that people can easily conceptualize. They can easily understand what you say when you use that word. When you say perspective, objects getting smaller into the distance, people instinctively know what you mean. And then you show them the curve calculator and say, well, this says it's going over a curve, but it completely ignores perspective. And the way it does it is to put you into a side elevation, remove you from the observation completely so they can maintain actual sizes. Now that might be a bit of a mouthful, but with enough repetition, people will start to understand what that actually means, how that magic trick's been done, how they remove you from the observation that they are comparing it to, so that they can exclude the narrowing of angles, the angle of attack, and angular size reduction at distance. They ignore all of it so that they can call it curvature. It's essentially hijacked perspective and called it curvature.
So what we can do is we can take back this standard refraction nonsense and say this is actually the limitation of the lens and the aperture, and we'll call it Airy's diffraction, but we'll remove that value off it and then say you can't have it because you can't even prove the thing that you're claiming, which is that the light bends in the first place to the extent that you say that it can. And more to the point, you can't prove that it bends over a curve. So what we should do is basically claim back standard refraction and claim it as Airy's diffraction and remove it out of the equation.
Well, it's not just that. The entire calculation is a hijacking of perspective. So while we're focused on one particular element, because that's what they go to, their go-to is the refracted hidden value. And in essence, it's ignoring this particular, very specific detail of Airy's diffraction. So when we can quantify it and say this is something that you can go out, you can test, you can examine for your own benefit, if it happens, it's already been shown. I mean, you said this off air the other day, Anthony, this debate's long over. We knew that in 2015 or 2016 for you, but we knew it, but there's people who come along every day that don't. And as we go through this journey arguing the same points over and over again, we find that we come across people like Zach, and he has his paint cans and a bit of an inquisitive mind to look further into exactly what is having happen in his viewfinder. And that is quite a magical thing to be able to say to somebody. It's not just a proof of nothing begging the question perspective omitting curve calculator that you must accept based on what someone's told you, i.e. you're on a ball to begin with. It's an actual demonstratable fact. You can go out and do it for yourself, like Zach has done. So I think that's probably about the roundest point I can end this on. So I'm going to say first and foremost a massive thank you to Zachary Zabala, which is YouTuber Good Times for All, which is GUDTIMS4ALL. So a massive thank you to Zachary Zabala. Thank you very much.
My pleasure, Nathan. Thank you for having me. It was a blast.
Yeah, I enjoyed it. I enjoyed it even more the second time. Having put the stills together, it was great to go through it because it's, you know, it's still new information to me and it's not 100% sunk in, but ultimately speaking, I know instinctively that it is what we are looking at from your explanations, even though they're not 100% cemented in my mind. So I do hope that you go on and do this presentation more and I will watch it again and again and again. So another massive thank you to you, Zach. And also a thank you to you, Anthony, for joining us. Pleasure as always.
Cool, man.
Short and sweet. And also a massive thank you to all of the live audience for tuning in and hopefully for sharing this discussion. If you hated the show, I'm sure you know exactly what to do, but if you liked the discussion and maybe found it interesting, share it with a friend, or maybe subscribe if you've not done so already. I've been Nathan Oakley, and I'll see you all in the next video.
Oh, what a day! What a lovely day!